iPhone 10, baby. All right. Here we go. So this is for all you people at home, the home video. You guys get to see it live. So you guys are really lucky. It's like seeing Led Zeppelin live back in the day. You can see, I saw Mr. Madden live. I didn't watch the video on YouTube. Okay, so this is the part that I'm going to ask you to not be talking while I'm talking, so the people at home can also understand what's going on. And also you can go and understand what's going on. Please, please, please take notes on everything today, because like I said, this stuff right here is what you're going to be doing for like the next 3 weeks. There's not a lot that we're going to add on besides what we're doing today. So we're looking at energy. And we're doing a little mind map about energy. So you need to have your notebook and pen or pencil in hand, because you're going to write this in your notebook as well. Energy. There was, somebody had energy of movement, and then other people called it something else. What is the energy of movement?
Kinetic energy.
Kinetic energy. Awesome. So that's going to be a big one that we look at a lot, because we're interested in things moving in physics. This is going to be kinetic. And with kinetic energy, it is the energy of movement. Does anybody know what kinetic energy is measured in, what the units are? Joules. Awesome. All of our energy is measured in joules. That's our unit of energy. And we're just going to make it a J in parentheses like that. Movement. So it has to have velocity. Does anybody remember the equation? Did you guys do this one in middle school? Kinetic energy? No? The equation. We're going to write it as, just in case you happen to go into AP Physics, how we write it in AP Physics. So it's a big E with a little tiny k subscript. So that's your kinetic energy. And that's going to be equal to 1/2 mv squared. Okay? Does anybody know what m is?
Mass.
Mass, awesome. And Riyadh, what's v?
Velocity.
Velocity, good. So this is mass. Again, that has to be in kilograms for us to get it into joules. So warning, warning, warning. And then velocity has to be in meters per second. Mass is in kilograms. So again, if we keep stuff in kilograms, meters, seconds, newtons, then we end up with joules at the end. Okay, kinetic energy, awesome. So what was another type of energy besides kinetic? I saw it written on a bunch of yours.
Potential.
Potential, awesome. And we're going to look at 2 different types of potential energies. Potential energy, and this is really the energy of what's called position. Having different positions that give an object energy, usually in some type of field. We're going to be mainly talking about things in gravitational field, not electrical field, until you get to AP Physics C, and we can talk about electrical field. This is also measured in joules. Potential. The 2 main types we're going to be looking at. The first one is, anybody know what this one is? If I go, oh wait, I want to do it over here. Twist the camera to follow me. Maybe. All right, I've got this mass down here on the ground. If you twist it, yeah. I've got this mass down here on the ground, and I'm taking this 2.5 kilogram mass, and I'm going, and putting it right there. Okay? What type of potential energy did I add to it?
Kinetic.
No.
Renewable potential.
Renewable, yes! No. What type of potential energy?
Moving. Gravitational.
Gravitational potential energy. Where's my button? Gravitational potential energy. You might see this abbreviated as GPE. We are going to use U, big U, which means potential, and a little g, which means gravitational. And we're going to say that is equal to mg change in y.
What's the U?
U means potential. So it's potential, gravitational potential energy. And M, any guesses?
Mass.
Mass, G,
Gravity.
gravity. And we're going to use 10 if we're doing equations. If we're doing any types of labs, we're going to use 9.8. So today, if we do any calculations, you're going to use 10 meters per second squared. And my change in y, what is that? Yeah, vertical position. So you guys actually might see that as mgh. Kind of the old school way to write it. Nowadays, we'd like to do mg change in y. So if this has a mass of 2.5 kilograms, and I raised it up, that's 0.8 meters, can you tell me the gravitational potential energy that is now stored in that mass? Do the calculation. Go. So the mass, that for my example is 2.5 kilograms. Gravity is equal to 10 meters per second squared. And my change in y is 0.8 meters.
So 25 times 7.
So, can you guys figure that out?
20.
20.
20 what?
20
joules! 20 joules, right? So, all I'm doing is I'm going UG is equal to 2.5. Sorry, I'll do it in order. Yeah, 2.5 times 10 times 0.8. And you guys got that equal to 20 joules. Okay? So it was 20 joules for me to get that weight on top. Now that it is up there, it has 20 joules of energy. Meaning, if I was to push it off and bother Mr. Willett downstairs, I just changed 20 joules of energy into kinetic energy right before it hit the ground. And when it hit the ground, now the energy's been dispersed. Okay, we have gravitational potential energy. There's one other type of potential energy. Man, I wish I saved some room down below. Well, you guys did the calculations in your notebook, I'm sure.
In my head.
No, write it down, 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 write it down. I don't want you guys coming and crying into me during cohort flex time. Be like, Mr. Madden, I don't get this stuff, and I have to redo this because I don't have anything done yet, and now I have to do this because you haven't taken notes during class. So, take those notes. 2.5, 10.8. Okay. Our other type of potential energy we're going to be looking at is called spring potential energy or elastic. Spring potential energy or elastic potential energy. Another way to see that, you could say, you might see it as EPE in some old school documents, or if you're watching some YouTube videos by somebody else besides me. EPE means elastic potential energy, which is the same thing as spring potential energy. It's a potential energy, so we can still use U, but instead of gravitational, we're going to use U sub S, and that's equal to 1/2 kx squared. 1/2 kx squared. Awesome question. Thank you so much. So many times I'm like, does anybody have any questions? And they say no. And I'm like, what's K? And they're like, I don't know. Why didn't you ask the question? Well, K. Okay. K is called the spring constant. And so let's take a look at my mass right here. I've got 500 grams on a spring. So if the spring is just like that, it has no energy. Okay? If I pull this down like this, now I've loaded energy in the spring, and the spring has energy to pull the mass up. Okay? So let's first talk about, what do you think X is? Here, yeah, but what is X?
Starting position.
And?
Potential energy in the spring.
No. Am I going to have more energy if I pull it from here to here, or from here to here?
The length of it.
The stretch, right? So X is going to be our stretch. Stretch, and we want that in meters, right? Because warning, 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 we want to keep everything in kilograms, meters, seconds, newtons, joules. K is called the spring constant. K is the spring constant. And the spring constant is in units of newtons divided by meters. N over M. And so what that is, if you guys take a look, I've got two springs here. My first spring, check it out, you ready, you ready, ready? Okay. Second spring. First spring? Second spring? What's the difference?
One has more
The
tension.
first one stresses more.
Yeah, so one is very easy to stretch, right? So this might have a spring constant of like 2 newtons per meter. This one is a lot harder to stretch. So it might have a spring constant of 20 newtons per meter. If you're looking at springs on like a car, like for shocks, you might have something like 10,000 newtons per meter, okay? So that's what that K value is. Kinetic potential. What about,
Electric.
electric, okay. Electric energy. Well, let's just throw some extras up here. Let's see, let's call type, other types. Other types. I'm gonna put electric, which we will get into the next unit. In level 5, you guys are gonna be doing electromagnetism, so electric circuits and magnets. So we have electric. You guys had a good one over here. Chemical energy. These guys said chemical energy, which is good. Where do we find chemical energy?
Batteries.
Yeah, batteries have chemical energy. Batteries. I heard renewable. Sure, ATP. That's easier to write than renewable, so I'll write that one first. ATP, what's ATP? Adenosine triphosphate.
What's that? We'll do that.
What, dancing?
Kind of. Like really good dancing? Is that why you said really good dancing? Or you just said dancing?
No, I meant like
Yeah, well, so it's where you get the energy in your cells, right? From the powerhouse.
Mitochondria.
Renewable energy. Renewable energies are different ways to get energy. We hit renewable energies a lot when we get into electromagnetism, because electromagnetism uses, all renewable energies use electromagnetism to make energy. What about, did anybody realize what song I was playing earlier? Halo singing it?
no.
No? Alright. Well, it's part of the work energy playlist.
It's called work.
Work. Work is a change in energy. Work is W, and it's equal to force times a distance. So a lot of you guys had force on your mind maps. It's not just force. Like force is not an energy, but if we have force over a distance, we can see how work is being taken or added to the system. So, like if I have this block, and I'm going to give it some kinetic energy. Why doesn't it keep going?
Friction.
Friction, right? So some force has been taken out of my system. I've added in, I've done work on the block, giving it kinetic energy. That slows down and stops. I know, amazing, huh? Is that amazing? Yes, amazing. Okay, so we see this a lot when we're dealing with friction. And so like the work on the block here was the force of friction times distance. Anybody guess what work is measured in?
Joule.
Joules, it is. Work is in joules because it's an energy. Work. One other one that we're going to use a lot to solve problems is called mechanical energy. And mechanical energy, we just abbreviate as ME. That's going to be equal to all of our energies together. So it's going to be the gravitational potential energy, if there is any, plus any spring energy, plus any kinetic energy. It is also measured in joules. So we use this a lot because energy is, what's that really famous saying about energy? Do you know any famous sayings about energy? Energy energy cannot be
Removed.
created or destroyed, right? It only transfers. So that is kind of one of the overall arching themes, is our law of conservation of energy, which says energy cannot be created or destroyed, it can only be transferred. And so when we look at our problems in this class for this level, we're going to see that energy is always conserved. Sometimes it's constant, and sometimes the energy goes somewhere, but it can always be accounted for. So law of conservation of energy says whatever energy we start out with at the beginning, we're going to be able to account for that energy at the end. And we're going to do that with what's called an LOL chart. Good. Let's do an LOL chart. Hey, Andy, can you move that camera so it's over on this board? And if you guys can't see, can you move to where you can see? Maybe can you guys move to this station? Can you bring it, maybe bring it to the middle? Or over on Jacob's table? You need to get a ruler. Please, get a ruler, get a ruler, get a ruler.
Why is it 2 times?
Because he wants it like that.
Please get a ruler.
Why don't you just put it here?
Huh?
It's gonna ruin it, no?
Why don't you just put it there?
Because it's in 2 times. Just gonna like shine it up a little bit.
In your notebook with a ruler, you are going to make an LOL chart. So this is the pro way to do it. Are you ready? So the pro way would be to like have your ruler across the bottom of your page, and then you're gonna go like boom. Like that, and then I'm gonna make, so now my L's are lined up.
The big lol.
What's the O?
So when we're looking at this, this is gonna be the energy initial. This is gonna be my energy final. And this O is gonna be my system. We're going to make 3 of these LOL charts today. Yeah, and it should be lined up LOL, not LOL. It's not a low L chart, it's an LOL chart. But here we go for our first one. What types of energies do we have? Potential, kinetic. So across the bottom, I'm going to go UG. US, EK. UG, US, EK. If you can't see, please position yourself to where you can see. And let's get something set up while you guys are there. Okay, here we go. Max, can you bring that camera so it's over here and you guys can see over here? Can you guys come on down so you guys can leave your notebooks where they are? Let's check out this little cool pendulum that I've got going on here.
Where I put it?
Maybe put it on this table. Ollie, can you move to the side so that... Actually, maybe from on the middle table might be better because then you can see the whole thing. Go over to the middle table.
I have to zoom out.
Yes. So, here's my pendulum. Right now it has 0 energy. I'm going to call the... so remember, gravitational potential energy has to do with position. And so I'm going to call this position 0. I could call this position down here 0, or I could call the bottom of the street level 0. But for what we're doing here, I want to call this 0. That makes my calculations a lot easier. And so what I'm going to do is I'm going to raise this up. Okay, and by raising it up, what type of energy am I adding to it? Potential energy. Awesome. So I'm adding potential energy here, and then as it comes swinging through the middle, that potential energy is changing into what? Kinetic energy, right? Then it turns into kinetic energy. It has maximum kinetic energy here, and then it starts going up. What happens to the kinetic energy? It's decreasing. What's happening to the potential energy?
It's increasing.
It's increasing, right? So we're gaining potential energy, losing potential energy, gaining kinetic energy, and back and forth. And that's kind of like how a pendulum goes. Now, law of conservation of energy states all the energy is conserved, so we shouldn't have any extra energy added to our system without anybody pushing it. So you should be able to come over here and hold the ball at your nose and stand really straight, and then you can let go, and it should come back, and it should not hit you in the face.
Can you try?
I need a volunteer.
Oh,
Okay, so you need to stand up tall, stand up straight. Yeah. So you're gonna hold it. So it needs to be against your nose, but you hold it. Hold it strong, tight. Okay. Now your goal. A lot of people do this, and they're like, "Oh, that's nothing." Your goal is to not move backwards. Also, not move forward. Though. Okay. When you're ready. So let go. Don't move. Don't move. Don't move. Don't move.
Don't move.
Out of here, Jensen. Move over a little bit, guys. All right, so hold it tight. You're gonna hold it tight all the way up to your nose. All the way up to your nose. Now you are not gonna move. That's the key. Don't move. Go. Oh, that was a good one. Good one. Nice one, Jensen. Hamza. We'll all have a chance. All right, hold it up tight. Harder, higher. There you go. Put your nose against it. Okay, there we go. Smell everybody else's nose, and when you're ready, let go. Don't move.
Don't move.
Then we're going to try. Any female volunteers? Get some ladies up in that place to be. All right. Now Riyadh has the advantage because he's taller, so it's going to be going faster. Right? He's got more potential energy stored. It's going to be going faster at the bottom. Ready? Whenever you're ready. Don't move. That was a great. You want me to get you? Can somebody give Rakan a video of himself? All right, so pull it tight. Pull it tight. Move it to your nose. Pull it tighter. Tighter. Okay, now your goal is to not move once you let it go. Don't move. I feel like you move forward a little bit.
لا احمد تركني
That's not the user, dummy.
Jacob.
Dina, you should do it.
Mr. Miller, why don't you do it?
عندي كمان.
What was that? I'm scared that you might break your nose. All right. So, one of the hardest ways to actually do it is closing your eyes, because closing your eyes, you really don't know like how far it is. It's really scary.
Which one do you try it?
That's scary. Anybody want to try eyes closed?
I'll try.
No.
I wanna.
Anybody else? Sorry, you can try. Eyes closed. Super scary.
Like you want it to be his face. He's so uncomfortable.
Close. Don't move. That bumped your nose.
Yeah, but it's on my nose.
Yeah, Rita.
You should do it.
Get up there. Try not to move forward, because when you let go, sometimes you go forward. But that's why Jensen's nose got hit a little bit. Okay.
Forwards.
لا.
All right.
I wanna try ice cream.
You can try eyes closed.
Forward with that.
Oh.
Higher. Yeah, you're good. Hey, I'm cheating.
ايش
Okay.
مالك انت فتحت.
So for our LOL charts, we're going to be looking at the pendulum. So the first part that we're looking at this pendulum, where we're going to take a look at our system, because we're dealing with gravity, we have to have Earth in our system. So in our system box, we're going to write the pendulum and the Earth. Then we're going to go from here is our initial energy, which is what?
Kinetic.
Potential energy. And that potential energy, my final position I'm looking at is here as it's swinging through the bottom. Oops, sorry. Swinging through the bottom, okay? So, come on back. off my bowling ball. All right, so my initial position is going to be
0.
on your nose, at nose. So you're holding it at your nose. The bowling ball at the nose, right? That's my initial position. My final position is going to be where h is equal to 0. So I'm going to call my height equal to 0 as my final position. The system is my pendulum and Earth. Pendulum. Pendulum. Now with a ruler, because of course you would use a ruler, you are going to, where is all my, do I have any gravitational potential energy? In my initial position, yes. Do I have any spring energy?
No.
Is there a spring there? Do you see a rubber band? Is there any elastic? Is there any workout bands there? No. So how much spring potential energy do I have?
0.
And at the beginning, when I'm holding that at my nose, what's the kinetic energy?
0.
So all I have is gravitational potential energy, and this is one of the only times we're going to be making bar charts in this class, so enjoy your bar chart. And we're just going to put some kind of arbitrary amount of energy here. And I'm going to say I've got 4 blocks of energy. 4 blocks of energy.
Can I have 5?
Sure. Yeah, you can have 5 blocks of energy if you want 5 blocks of energy. Now, as it goes across the center, it's coming down, and as it goes right through the middle, does it have any gravitational potential energy? No, right? We said 0 was at the bottom. So it's got 0 gravitational potential energy. Ahmed, is there any spring energy?
No,
Good.
there is kinetic energy.
But there is kinetic energy. How much kinetic energy?
4.
All of it. All of it got transferred to kinetic energy. So now in this case, all of my gravitational potential energy was transferred into kinetic energy. This is considered conserved. Why is it conserved? Because it's always conserved. There is a law of conservation of energy. And in this case, it is also constant because the initial energy is equal to the final energy. Okay, we're starting to get it. Now, this is used as an analysis, so now we can actually figure out what it means algebraically. So, I know that all of my, one of the things we like to ask when we're doing this is, where did the energy come from and where did it go? That is so important and it solves so many problems. I want us to actually write that here. Energy, where did it come from? Where did it go? Okay? Over half of the problems, I would say 99% of the problems here, we're asking where did the energy come from and where did it go? And using that, we can solve for different problems. So now, here I say, where did the energy come from?
Gravity.
UG. Where did it go?
GK.
Now, we have equations for these, don't we?
Yes.
What's my equation for gravitational potential energy?
mg change of y.
What's my equation for kinetic energy?
Half mv squared.
Yeah.
Yeah.
Half is
Now, do you have to memorize these?
Yeah.
Heavens no, why?
Equation.
They're on the equation sheet. Okay, so you don't need to memorize these, but you need to know how to use them. So, what I would like you to do now, big challenge, go back to your tables, and I want you guys to solve for the the velocity, how fast this bowling ball is going as it goes through the middle. Now, what do we need to know?
Mass.
Mass of the bowling ball is equal to, Riyadh, what does it say on the side of that box? Is it 6.4 kilograms? On the side of that box? 6.4 kilograms. What gravity are we going to use?
10.
My change in y, most of the time, since I called this 0, Nasser, can you hold that there? Hold the meter stick. Because. So, if this is 0, hold it still, I'm going to lift it up 40 centimeters. 40 centimeters. So my change in y is going to be 40 centimeters. I want you to go back to your tables. Go back to your tables, and I want you to solve for the velocity of the bowling ball as it's going through the middle. Okay? Go. Yes. So go back to your table, Ali. Go back to your table, whoever's at other tables. Huh? Good. Do it in your notebook. Rakan, you want to do it? You're doing it on the board?
Mr. Madden, can I erase this?
No.
40 centimeters?
This. Riyadh.
Yeah.
Move.
Haha.
Still
We're
using it.
working on Ali's one. Yeah.
ماذا؟
مالك انت؟
ما الوضع؟
مالك انت؟
يملع.
مالك
العب عليك. ليش بتعصب علي؟
علي تعبان اليوم.
Eugene is equal to. Well, Eugene is.
It's the gravel.
Just 4.
Oh,
We have 4 bars.
it's 64 times 4. What? Oh, it's
6.4.
no, 64 times 4. So it's 64 times 4. Let me find my calculator. 2,500.
Yeah, what?
Joules, yeah.
Yeah.
Riyadh,
Yeah.
you have to change centimeters into meters.
Centimeters?
You have to change it into meters. Oh, wait, this is meters. This is meters times.
Yeah,
Change it to centimeters.
so what you do is that 40 centimeters is equal to 0.
Jensen,
So you do 64 times 0.4.
No.
Senior bud.
Just taking it.
And then swimming.
Times 0.4.
what is 25.6? I'm
Yeah, that's what we're going to hold that.
Are you in
What
like
the hell you
2,560?
What is it?
This is not. Oh. 2 times.
Hey!
خلاص عادي. Wait, Mr. Madden.
Isn't this the below?
Did you get 20?
Yeah.
Mr. Madden?
Yeah.
That's 64 times 10 times.
Use your calculator.
Yeah.
Mr. Madden? Wait. Is it 6.4?
Mr. Madden, 6.4. What's the
Oh my god, I saw it. 64.
Okay. All right. Back up, you punks. My board. Wait, I shouldn't do that on camera. Never mind. Can you guys please move for a little bit, and then I'll show you guys how it's done. All right. Good. I think you guys got it. Hopefully nobody fell into my trap.
Centimeters and meters.
Yeah. Thank you for catching my trap. Remember, we have to keep things in kilograms, meters, seconds, newtons in order to get things in joules. So my trap I set for you guys was I put 40 centimeters, which I have to change that right away to what?
24.
0.4 meters.
24 meters?
0.4.
Yeah, 0.4 meters, good. Okay, so the way that I like to do this is I like solving for the variable first. That's the kind of like higher level physics version, is solving for the variable first, then plugging in the numbers. If you plugged in the numbers first, that's totally cool, as long as it works for you. So the way I'm gonna start it, I think Rakan has a good way that he did it here. He plugged in the mass, gravity, the height or the change in y, then he did 1/2 6.4 v squared. He got that down, and he got square root of 8, which I believe is correct, 2.3. Riyadh also got the same thing over here. Let's check something out that's really cool that works if everybody brings mass to the party. Okay? Now I have this equation, mg change in y is equal to 1/2 mv squared. If I have mass on both sides, everybody brought mass to the party, what can I do with the mass?
Divide it on both sides.
Divided by both on sides, which does what? It eliminates it.
Each other out.
I can only do that if I have mass in every term, okay? So now I've got g change in y is equal to 1/2 v squared. Multiply 2 on both sides. 2g change in y is equal to v squared. And I know I can square root both of these. To get v is equal to the square root of 2 times g times change in y. 2 times 10 is 20.
Change in 1.4.
Times 0.4. 20 times 0.4 is equal to 8. I also got square root of 8, which, if you do your calculator, I believe it's 2.3. Let me check that. 2.3. 2.8. 2.8 meters per second. Awesome. That is crazy that we can figure out how fast that bowling ball is going at the bottom. Right? That's really, really powerful prediction that we can make. Good. Okay. We're not going to do any more calculations with the rest of our LOL charts. I just want to show you 2 other examples of how they work. Any questions on this so far? No. Good. Yeah.
If I do mg and add 13 to one, is that fine?
اه غشيت مني.
Oh.
They don't even have a mark.
Okay. Can you guys make another LOL charts the same as before?
Give back my marker when I crack.
Lollipop.
Can you guys get a, we're going to do another LOL chart. So can you guys make another one either below?
I need my marker back.
You don't need a marker. Go, where's your notebook?
Please use the magic word.
Use the magic word and go use your notebook.
No.
No more for you. Say please.
I need my marker back. You're not a good boy.
Okay. So, now what we're going to do for our second LOL chart. For our second LOL chart, I'm going to start at the same position. But now what I want to know is what the energy is there. There.
No.
So before it gets to the very top, after it's gone through the middle. So, my initial is still going to be like when I'm holding it at my nose. My final is going to be it's going to be such a good video for everybody to watch at home. My final energy is going to be past h equals 0 at h equals 0.2. And here we said nose at h is equal to 0.4. That's meters. Meters. So in the beginning, this says at nose, 0.4 meters, right, where we started it. Energy final is after it's gone through the middle, it starts coming back up, and it's at 0.2 meters, so not all the way back at 0.4 meters. So here, at the beginning, where does the energy come from?
UG.
UG, and it's all UG, right? So it looks exactly like our first one.
4.
So 4. So yeah, make 4 bars, or if you made 5 bars, make it the same. My system is going to be the same, it's just the pendulum in the earth. Now, in my final position, do I have gravitational potential energy?
No.
No.
Yes.
Right? It's
Like the small business.
so we started out with my pendulum here. This is the middle when it's here, and I'm asking for it
Oh yeah, yes.
when it's right
Yes, you
here.
do.
Yeah.
So does it have gravitational potential energy?
Yes.
Yes.
Awesome. Does it have spring energy?
Yes.
No.
No. There's no spring, there's no elastic, there's no rubber bands. Does it have kinetic energy?
Yes.
Yes, it's still moving. So now we have to split it up, and it's up to you in the beginning, like how you want to split it up. So if you do 2 and 2, that's fine. That makes sense to me.
He was on the little computer trying to come down. No, that's so fun. I wish I want to go see. I was gonna go myself.
Okay, so where did the energy come from?
Potential.
Where did it go?
Potential and.
Potential and kinetic. Okay? In this situation,
Myself.
Ali, is my energy conserved?
Yeah.
Yes,
Yeah.
why? Because it's always conserved. There is a law of conservation of energy.
Yeah,
Is it constant?
no.
No.
Does the amount of energy in my initial situation equal my amount of energy in my
Yes.
second?
Yes.
Yes, so it is also constant. And we said, as Max said, where did the energy come from? UG is equal to UG, maybe UG final, plus EK. Hey, Nasser and Hamza and Ali, sorry, you guys move so these guys can see a bit.
Oh, you gotta win the video all the time.
So now I can make my new equation from this, which would just be like mg. I'll use h this time because they kind of are interchangeable. Or change in y. I'll use change in y. Change in y initial is equal to mg change in y final plus 1/2 mg squared. Okay, and that's as far as we're going to take that one. So now if we knew this, like we could actually solve for the velocity. If you want to solve for the velocity of the ball at 0.2 meters, go for it. Otherwise, I'll give everybody else a minute to copy the rest of it.
We're gonna do another one, right?
We're going to do one more, just like this. We're not actually going to do the math on it.
So we solve now?
Nope. If you want to solve for at 0.2, let me know. My initial would be 0.4. My final would be 0.2,
Huh?
and you could solve for.
No, wait.
Okay. Good. Last one. Can you please draw one more LOL chart? My initial situation is going to be the same. Same.
Just give me your back.
It's with you.
Interlude.
Does he stop?
It says stop. So my initial is going to be the same. My final is going to be, oh, look at it. Call that stopped, right? It's stopped.
What did?
The ball. What?
Oh, yeah.
Newton, he's not moving anymore back there. Finally.
It is.
Well, let's pretend it's totally stopped.
Okay.
Can we pretend? Okay, so I've gone from initial to EF, the energy final, where it's totally stopped. In the beginning, I just have my same gravitational potential. It's at my nose. I let go. After a really long time, it comes to a complete stop. At the end, does it have gravitational potential energy?
Yeah.
Yeah.
No.
No, we said H was 0 at the bottom. Does it have any spring energy out there?
No.
No. Does it have any kinetic energy?
Yes. No. So there's nothing.
Oh yeah, 0.
Nothing. It's 0. It's not moving.
Stop.
Constant.
So, but where did the energy go? We have to show it to that it is conserved because it's always conserved. So what we do is we show the energy leaving the system. So I need 4 bars of energy
Leaving ball.
leaving my system.
And you're not, right?
Where is it going?
Not supposed to do it.
Where did that energy go? Why did it stop?
Went to the air.
What do you mean by the air?
Friction from the chain.
Friction from the, yeah, right. So we have friction in the chain. We have air resistance that's being taken, taking this out of the system. Also, listen.
Sound.
Right? It takes energy to make that noise. So it's losing energy through air friction, sound energy, and what is that called when we change energy?
Transformation.
What is it called when we work, right? So I would show Ahmed and Ali that the energy is coming out, and I would say that's due to work by friction.
Friction. What if friction is unemployed?
Yeah, good. I like how you know the word work 2 different ways now. That's awesome. Okay, so is it conserved?
No.
Well, yes.
There is a law of conservation of energy. It is always conserved. There are 4 bars here. There are 4 bars here. Why is it not?
Because that one.
Yeah, facts.
Yeah, there we go.
E initial is not equal to E final.
Wow.
So my equation for this one would just look like UG is equal to work done by friction.
I was just joking there, but I think about
You can just write WF.
Sure. Okay. Good. Now, I would like to show you the most wonderful device for energy ever. Also, notice my cup that was given to me by Bennett for Christmas. Thanks, Bennett, for the present. Does everybody understand it now? I have potential, right? Just like work has 2 meanings. Potential. That's called a double entendre, I think. I think that's what a double entendre is.
What?
Huh? Is that a double entendre? I think that's a double entendre. I don't know. I'm not an English teacher. Come on. Okay. One more thing. Who's got their phone? This is not a trick question. Me. Good. You guys got your phone? Actually, let's put this back over here then for this one. Can you make sure it gets the floor and the... Okay. So I've been working out a lot lately. So I don't know if you guys know that. Well, I know you can tell. Ripped. But I got my mass on the floor. Okay. Can somebody time me how long it takes me to get it onto the table? You got it? So I'm going to say go, and then you're going to stop it when it hits the table. Ready? Who's got me? Who's got my timer? Me. You got it? Ready? 3, 2, 1, go. 3.69. Let's round that up to 5 to make our calculations easier.
Why?
Yeah, let's round it up. So, we have that. So, can you write down 5 seconds for my first time? Second time. Let's try that again. Now that I'm warmed up. Ready? 3, 2, 1, go.
1.25.
Awesome. Let's round that to 1. Okay, there were two differences there, but it was the same amount of energy. The time was different. And we need a way to show that. And the way that we're going to show that is, can you guys back off a little bit there, Ollie? That is called power. So please add one more thing to your list. That's called power. You move over that way so the flat home can see it. Power. Power is big P. Ollie, big P is equal to, where's your notebook?
I took it from me.
Change in energy over time. Can you tell me my power for the first time that I did it and the power for the second time that I did it? So that my time for the first one was 5 seconds. My time for the second one was 1 second.
E equals change.
We already calculated that.
E divided by T.
You guys calculated it earlier on in class. What was the energy that it took for me to move that up?
20 joules.
Alright?
20 seconds. 20 joules.
20 joules
20 joules.
was the energy.
You already have the time, Jacob.
What was my initial time?
5.
Oh, sorry, yeah. What's my initial power then?
That's just close.
I like you guys stop talking when I'm talking. That's the third time I've had to talk to you guys today. And that's on video. Right? So if we have to have a meeting later, I'm going to come back to this part to show that you guys have been talking and how annoying it is throughout the entire class. Okay. Okay, power. What's my initial power, Ollie?
20.
No, wrong. Stop. No, figure it out.
5.
It's initial, and it was on.
So, power is what's my equation? Change in energy divided by time. So my change in energy was 20 joules. The time was 5 seconds.
4.
For what's the unit for power?
Joules?
Yes.
Joules.
What's the unit for power?
Watts.
Watts. All right, for my second one, what is my power?
20.
20 joules divided by 1 second.
20.
20 what?
Watts.
Okay, 20 watts. So I have more power if I do something faster. Now, for our last thing of the day, the best physics example of energy you will ever see in your entire life. No. So, I have two examples of this. The first one, my daughter's been playing with a lot over the last 3 years, and so it's kind of on its last legs.
Don't break it.
It's kind of already broken. So, I want you to watch this and think about all of the physics that is going on in my Hello Kitty ladder. Sometimes I need a little help to get going. Come on, guys. They need a little bit of help sometimes. They're old. I got this, I think, 4 years ago down in the market next to the Grand Mosque. Thinking physics. We're thinking.
It's falling there, one of them.
Oh no.
That would not keep
Got a little stuck there. Okay. That's you know, that one's been around for a while. So this summer I went and got this one for you guys. So you can see how it really works. This one's guy's going backwards. I've never seen him go backwards before. She's riding the switch.
How you feel?
So now, actually, I actually really like the song from the other one, and this one actually has a cool switch where it can keep going, so you can play the music that you want to play. Okay, now that you guys know energy, and we have this huge energy mind map of what's going on, what types of energy can you relate to what we've talked about today? Mikhail, what's one thing that you see that we talked about today that relates to this? Potential energy. How are we getting potential energy? Right, so the movement, the penguins are getting potential energy as they come to the top. Jacob, what's something else? The potential energy, where did it come from? Potential energy is going into kinetic energy. Jensen, what's something else?
They lose the speed as they go.
Right, so work is happening by friction as they're going down. They're not going as fast as they should be because some energy is being taken out of the system. Riyadh? No, I don't think so. No, they're coming down! Where else? Mechanical power from the ladder?